our self-test on our qualitative analysis practice questions. So the first one is a bit of an intro. We've done a few questions like this before already, and really it's just getting to know the complete ionic equation, ins and outs, and the net ionic equation. All right, so we're going to go over question one, starting with A. We're asked to draw a diagram of this mixture. So we've got a mixture here, and we've got a mixture of lead to nitrate. Okay, lead 2. Lead, I remember, is Pb, and that 2 indicates that it is a lead valence with a positive 2 charge as opposed to a positive 4 charge, because lead is multivalent. So we have to specify we're talking about lead 2 or lead 4. They have different colors, they have different reactivities, they have different properties in general. They're almost like they're different elements, really. They're almost as different from each other, in some ways at least, as, say, iron 3 is from lead. Now, not in other ways, obviously, but what's important to recognize is they're very different despite the fact that they look very similar and they have the same number of protons, which is why they're both called lead. But they're sufficiently different that we have to always specify what we're talking about here. And it may seem like a small detail, but it can make a big difference. So we've got lead 2, okay, so that means Pb2+. And we've got nitrate, which we've seen a lot by now. So if you weren't sure, you could check on your ion table, but that's nitrate. And iron 3. So we know iron is Fe, and we just talked about how this Roman numeral is the valence of that charge. So iron 3 is very different from iron 2, and that's significant when it comes to dietary iron, because one of them is is easier to absorb in your stomach than the other. But often iron pills are in, I forget which one is the one you can absorb easily, but I remember that it's often not the case that the iron pills are the ones in this right valence. You have to eat iron pills with things like vitamin C and greens so that it helps to convert them. All right, and chloride ions like so. Okay, so we're going to draw a diagram of a solution. And that solution has lead in it, so don't drink it. And it's got some nitrates in it. And it's got enough nitrate to balance out. There's twice as much nitrate because they have -1 charge and lead has a +2 charge. So there's twice as many nitrates as there are leads. And we've got this iron 3. So we've got an iron 3 in here somewhere. And it looks like we have 3 times as many chlorides as irons, because these -1 charges have to add up to balance a +3 charge. Okay, so there's our solution before anything happens. And I'm going to leave some space here so I can write an after picture if I want to, which I do want to. All right, so we'll move on to question B. We're asked to write out the complete ionic equation. So when we mix these together, some Pb2+, which is aqueous, and some nitrate, which is aqueous, and I guess there are 2 of these compared to 1 of these, and I'm going to add that to some iron 3+, aqueous, and 3 chlorides, also aqueous. Okay. Now, maybe it's true that some of these react to form a precipitate that's going to sink out of the solution. So before I move any further, I'm going to just go to my solubility table and check any of these compounds pair together to make an insoluble, or at least a low solubility compound that'll form a precipitate. And I don't know, maybe, so I know nitrate, I've seen it before. I know nitrate is always soluble. So nitrate is a red herring. So I'm going to stick to chloride. I'm going to try and find out if chloride will bind either with lead or with iron to form a low solubility compound. So chloride, I would look here and say, oh, lead 2. Hey, I've got lead 2. iron 3 doesn't. Iron 3 would be up here. And worth mentioning, so would lead 4, Pb4 plus, the other valence of lead. The other valence of lead is not a low soluble compound with chloride, but this valence, Pb2 plus, lead 2, will form a solid precipitate with chloride. So we got this Pb, and we need 2 chlorides to balance that. And that's going to be solid, so it's going to drop out of the solution. And we're going to have these left over. What are we going to have here? We're going to have some iron, and it's aqueous, and some nitrates. Okay. Now, we can get into a big issue with balancing all of the ions in a complete ionic equation. So I don't actually want us to be spending that much effort doing this, because right now we get this problem with we have 2 chlorines here, but 3 here. So actually we need a 3 here, which means we need a 3 here, and actually we have to change this to a 6. But we already know that a lot of stuff's going to vanish out of solution, and so we are only concerned with the simplest reaction, which is going to be our net ionic equation. And when we get that, we're able to simplify those back down anyway. So actually I'm going to ignore that for now. I'm just going to write my lead aqueous plus our chloride, which is aqueous, and that's going to form lead chloride, which is solid. And we're really going to reduce each of these coefficients. We're going to divide them all by 3, because they're all divisible by 3, and we can write a simpler ratio, which is 1 lead for every 2 chlorides makes 1 lead chloride. Okay. And for question D, we're just going to state the precipitate, and this precipitate is lead chloride, solid. So I might write an after drawing, which shows that our lead ions are binding with our chloride ions. And up here, we'd have some leftover nitrates and irons. So, and they're just floating around in solution. Okay. So that's a kind of basic intro question. And if you can get through this question, I might go back to the question on Google Classroom you were asked on Friday to try and decide on a compound to add to a solution that would bring out, I think it was hydroxide, if I remember correctly. And if you understand this, you should really easily be able to answer that question. And of course, recognize you have to add a compound. You can't just add an ion. All right, so let's move on to question 2. Question 2 says you have 3 unlabeled test tubes. 3 unlabeled test tubes. And they contain iodide, copper, and calcium. Okay. And we want a procedure that we can use to figure out which one is which. Okay. So I might draw a diagram here. All right, question 2. I've got these 3 test tubes. This is my iodide test tube. I've got a copper test tube. And a calcium test tube. All right. But I don't know which one's which. Which one is which? So they all look colorless. Well, they don't actually, because copper 2 is blue. So we're going to pretend maybe we don't know that. You probably didn't know that. Maybe you did. And we're going to talk about how to test maybe thinking of some sort of chemical test we can make. So we're going to think about things we can add that will form a precipitate using our precipitation principles. In one, but not the others. So what kind of substance can we add that will form a compound that will take out, say, calcium, but not copper and iodide? I noticed. So actually, there's a few ways we could go about this. I can already see a few. Now, my intuition tells me that iodide is different in these guys. It's a negative charge. So my intuition tells me if I add some nitrate, I can maybe precipitate out the iodide first. Now let's just see what we can add here. Maybe we can get some sort. Iodide forms a low solubility compound. With lead, copper, and silver. Okay, maybe that's not a great idea, because then we're going to add lead, copper, or silver, and that's going to somehow contaminate the other ones. So maybe we can think of something. I would ideally like to be able to figure out something I could drop in each of the beakers, and then each of the test tubes, and then figure out one that makes a precipitate, take it out, label it, and then find something else I can drop into the other ones. But I guess I don't have to do that. I could go other routes. So I'm just going to look and see if I can think of anything else here. All right, so I can see that, all right, what am I looking for? I can see a calcium ion here. Okay, so if I add sulfate, it's going to bring out the calcium, for sure. And then I just have to discriminate between copper and iodide. So let's do that first. So what I could do for step 1 is I could take a sample from each. A sample from each with okay, I want to mix sulfate, right, to take out the calcium. But I can't just add sulfate, so I'm going to add a neutral ion, positive ion, like sodium. So sodium sulfate. So we'll mix a sample from each with a sodium sulfate solution. And this will, so the calcium, Ca2 plus, sample will form a calcium sulfate solid precipitate. Okay, so then you want to remove and label the calcium test tube, because we just found that we took a sample from each. So a sample and we've labeled it, and we called this, maybe we put a little tape on there, we said that's A, and we called that B, called that C, and we'll take a little sample out of here and we'll call that sample B. B, sample, and this one, again, we'll call that sample C. Okay, and we just found that sample A contained calcium, and these guys didn't, so we'll remove this guy. Okay, so now, step 2, we only have sample C, which happens to have iodide, but we don't know that. and sample or test tube B, which has copper in it. And we also still have these samples, but we don't have this one anymore. And we have sample B, C, sample C, this is sample B. Okay. So now we need to add something that's going to bring out copper, or form a precipitate with copper, but not iodide. Let's take a look. And so we're tempted to use copper 1, but as we talked about before, copper 1 is different. This is not what we have. We have copper 2. They do not react similarly. And I can't find anything that specifically binds to copper without binding to other positive ions. So maybe I'll take something, add something that, well, I guess I could add sulfide or hydroxide. And that's going to, adding hydroxide is not going to bring out any iodide. So I'll add a hydroxide ion and I'll add some sodium to it. So I'll mix that sample of each remaining, test tube with a sodium hydroxide solution. So the copper 2 plus solution will form a copper hydroxide solid precipitate, just like in Howe Sound at Britannia. They had hydroxide, right? They used calcium hydroxide, the same principle. And so we'll remove and label the copper test tube. And then we're kind of done. We've sorted them all because the remaining test tube contains iodide. It must, right? Okay. And that's how we work through a question with several mystery ions in solution. Okay. Let's move on to question 3. Okay, so an industrial sludge. Okay, here's where we get interesting. An industrial sludge contains some iron ions, calcium ions, silver ions, and beryllium ions. So we're going to outline compounds that could be added and in which order so that we can precipitate and filter out each ion. Okay, so this is going to be really similar to our third example. Let's see what we can do here. So we're starting with solution that's got some iron ions, calcium ions, silver ions, beryllium ions. There are other things as well. We're just going to focus on these because there's negative ions and there's water. Okay, so we're going to see if we can figure out what we can do to subtract each of these from the solution one at a time and form a precipitate. So what forms a low solubility compound with just one of these compounds but not the other 3? Okay, so I can see a few options, I think. I think sulfate will react with silver. Oh, but it will also form a low solubility compound with calcium. So sulfate is out. But, oh wait, hang on. Chloride will form a low solubility compound with silver, but not lead or copper. Pardon me, and lead and copper. We don't have any lead and copper, so actually maybe chloride or bromide or iodide could be added to, and it'll just take out the silver. Okay. So step one, I'm going to actually draw this in diagram form. Step one, we're going to add, we can't just add chloride, we have to add a compound. Something that balances the negative charge of chloride with some positive charge. And I don't want to add a base or an acid, so I'm actually going to add sodium ions because they're cheap and simple, and table salt is cheap. So add a sodium chloride compound. Okay, and then we get, as a result, we get silver chloride at the bottom, solution, pardon me, solid, and we have these other guys still floating around. In the solution. All right. So step two is to filter AgCl, solid. So that means we're going to put the whole thing to a filtration. So, of course, I'm trying to draw a diagram. Don't worry too much about the diagram. I'm trying to draw a diagram of this as a profile. It's a funnel. It's got a filter in here. All right, and it's going to catch all this solid silver, and all the rest is going to float into a new beaker. All right? And so it's going to have all of the other ions in it, calcium, beryllium, iron, but none of the silver chloride. Okay, so that's step one. So then we're going to move on to try and remove another one of these ions. So what can we remove now? We've got calcium left, beryllium, and iron. Now I seem to remember we saw something we could add that would take out calcium. We talked about it when we were trying to select one to add in step one. And yeah, it looks like we could add sulfate. Sulfate looks like it removes calcium, but it doesn't look like it will form a low solubility compound with any beryllium or iron compounds. Beryllium. Hang on a second. Okay, now I can see it. All right, anyways, so that looks like we'll have to add a sulfate compound. So step three is we are going to, oh, I forgot to mention, we've still probably got some silver in here, ions. I forgot to mention that. We added, pardon me, sodium ions, so we should have some sodium ions in there. All right, so step three is we're going to add a sulfate compound, but we should add some positive ion to balance that. So it's going to be a sodium sulfate, maybe. Add Na2SO4. And it could be a solid. Actually, it could be a solution as well. It doesn't really matter. All right, and so what's going to happen there? Well, that means we're going to have, that's a terrible beaker, janky old beaker, and we got some, oh wait, so we said that would bind with the calcium, so that gives us calcium sulfate solid. And what do we have left? We've got some sodium ions, some beryllium ions, and some iron ions. Okay. So then, step 4 step 4 is going to filter out the calcium sulfate. And so I'm not going to draw the diagram this time. Well, I'm going to draw a diagram. I'm not going to draw a diagram of the filtration. Actually, no, maybe I will. It's going to be a simplified version. And so we'll have this filter. And I'll have all of our calcium sulfate in it. And in our solution, we're only going to have our sodium and our beryllium and our iron floating around. Okay, and now we're going to need to add something that's going to take out either beryllium or iron without taking out the other. All right. So what do we have here? Beryllium and iron. So what I do notice, if I look for a while at this table, is if I add sulfide, looks like it will form a low solubility compound with all other ions, but not beryllium. Beryllium is soluble in sulfide ions, and so are all the alkali ions, like the sodium. So actually, it looks like we'll add a sulfide compound. So we'll add, this will be step 5. We'll add sulfide, and we've been adding sodium with our ions, so we'll add sodium sulfide. And that's going to create a, what did we say? Iron sulfide solution. 2s3, that's going to be solid. Oops. And what are we going to have left? We're going to have sodium ions, and we're going to have beryllium ions. Okay. So then we're going to go on to step 6, which is to filter out the iron sulfide. Okay. So we're going to have a filter. And it's going to have all of our iron sulfide in it. And in our last beaker, we're going to have our sodium and our beryllium. So now we need to take out beryllium and leave the sodium. So for step 7, a lot of steps, we can go to our ion table and say, well, what's going to take out beryllium but not sodium, not an alkali ion? Okay. And it looks like a lot of these compounds are going to take out things like beryllium, like hydroxide, or any phosphate or carbonate or sulfate, and all of them are soluble with alkali ions. So we'll choose, we did hydroxide last time, maybe I'll choose sulfite, yeah, why not sulfite? We haven't done that yet. So add some sodium sulfite. Add sodium sulfite. And that's going to form some, what is it going to form? Beryllium sulfite. And we'll have left in here just sodium ions. And lastly, we'll step 8, filter out the beryllium sulfate. sulfite. And so we'll have this. And so we're going to catch in our little filter here all of our beryllium sulfite, pardon me, and leaving a sodium solution, like salt water, basically. Okay, and that is how we isolate each of these compounds individually. Now, your mileage may vary. Maybe you found another way. That's fine. There's lots of different ways, probably, to go about this. I was trying to choose what I found was a pretty streamlined method, and you may find another method. And this is the sort of thing we're going to be doing on next week. I said Monday, but some part of me is telling me it's going to be on Tuesday. All right. So moving on, last question. So we've got a solution that contains both sulfate and hydroxide. Okay. We want to make an experimental procedure to remove each ion individually. Identify the reagents using this procedure. And we're going to write net ionic equations for any precipitates formed. Okay. All right, so we've got a solution. I'm going to draw a diagram of that. Looks like it's got some sulfate ions and some hydroxide ions. Okay. So we're going to add something that's going to react with sulfate, but not hydroxide, or vice versa. And so what can we do here? Looks like we've got a few options. I'm going to try to add some. So it looks like, I noticed that strontium is soluble with hydroxide, but has a low solubility with sulfate. So maybe I'll add some strontium. All right, but I have to add a negative ion as well to balance that out. Well, I guess if I know that strontium is soluble with hydroxide, maybe I'll add some strontium hydroxide. So I'm going to add some, so step one, we're going to add strontium. Is it cheeky to add hydroxide? You know what, maybe I won't add hydroxide. So maybe instead of strontium, I could do it, there's nothing wrong with it, but maybe I'll do strontium sulfide. Let me think about that for a second. So if I had strontium sulfide, then I'm going to have sulfide in the reaction as well as hydroxide. So if I add anything to take out the hydroxide later, it might also react with sulfide. Oh, right, unless I add more. Okay. Maybe. I think this is okay. Strontium. Oh, wait, here we go. No, okay. So every positive ion that I can add is going to be soluble with everything else, in low solubility with everything else. Wait, is there any ions that are going to be low solubility with hydroxide that are soluble with others? You know what, I'm just going to add some strontium iodide, why not, strontium chloride, and let's just see what happens. So it's okay not to necessarily know what happens here. So I'm actually going to add, realistically I would probably add it in a solution. instead of solid. But okay, so I'll add some strontium, and then what is that supposed to form? I forget now. I was thinking too hard there. Oh, it's strontium sulfate. And then that means I will have some chloride ions now and some hydroxide ions. Okay, now I need to find something that's going to bind to hydroxide and form a low solubility compound, but not iodide. Or not chloride, pardon me. Let me just think about that for a second. Is that going to work? Anything I can add that's going to bind here, except for those. There's no overlap between these things and those things, which means everything I add is going to take out hydroxide. It's also going to remove chloride. Okay. Yeah, so that tells me that adding strontium chloride was a problem, because now there's no way I can remove hydroxide without removing chloride first, unless I do another step where I add some other ion. I don't know. I think we're just running into a problem where we kind of have to, when getting rid of a solution, add hydroxide. So I think I got to go back and imagine I added strontium hydroxide. Let's just pretend we did that then. This is why we do it on paper before we start mixing chemicals together. Okay, so that means, in fact, I won't have all my strontium and sulfate will bind out here into a precipitate, but my hydroxides will be left. And I will, at step 2, filter out our strontium sulfate. All right, so we're going to have a big filter here. And out is going to flow just a hydroxide solution. And now we need to get out that hydroxide, so we're going to add something that binds to hydroxide. We've seen a lot of metals that do that. So I'm going to add copper, because that's what they do at Britannia Mine. So I'll add some copper ions. But what can I add that's going to bind to hydroxide? What's copper soluble with? Copper 2 is soluble with sulfide or chloride. So I'll add copper, some chloride anyway. So what's it going to be? Well, I guess I could have kept the chloride in. I guess it didn't matter. No, wait, it did then. All right, so then I'll do copper hydroxide. Add copper hydroxide. No, not copper hydroxide. Chloride. That's what we were saying. And that's going to form a copper hydroxide precipitate. And it's going to leave some chloride ions in the solution. All right, and lastly, we need to filter out our copper hydroxide. So we're going to put our copper hydroxide in here. And that leaves us with a solution that only has chloride ions in it. Okay. All right, and that's question 4. All right, so good luck with those. Let me know if you have any questions about any of those practice. And those are good ones to practice and feel like you really got, because we're going to be doing some planning and some labs next week that are going to require us to understand that idea. those ideas.